alcohols can be synthesized via addition reactions of alkenes, and depending on the reaction you choose, you might get what we would call the Markovnikov reaction or the anti-Markovnikov reaction, which refers to whether or not the OH group gets placed at the more substituted carbon. We call that Markovnikov addition, or if the OH group gets placed at the less substituted position, that is termed the anti-Markovnikov addition reaction. And when I'm talking about substituted positions, I'm referring to the alkene, right? This would be considered the more substituted carbon, and then the less substituted position. Okay, so there are two conditions that can be used to do Markovnikov hydration of an alkene to produce an alcohol. And the reason why this is called a hydration is because overall we're getting addition of OH and H. And when you look at OH and H together, that's really just water, so it's called a hydration. These reactions were initially covered in Chapter 9, so if you need to review those, you can go back there, right? But you can either use dilute sulfuric acid to do Markovnikov hydration of an alkene, or you can use a reaction that's called oxymercuration demercuration. The advantage of using dilute sulfuric acid is that it's a less expensive reagent, and it's not as toxic as using a mercury-based reagent. But the disadvantage is that it goes through a carbocation intermediate, and that carbocation may undergo rearrangement, which could be an undesired outcome. You can use oxymercuration demercuration, and the reaction does not go through a carbocation intermediate, and so then that carbocation that isn't formed, of course, will not rearrange. We'll look at that a little bit in more detail when we start talking about the mechanism. And then the last reaction we'll review is hydroboration oxidation. And that provides, again, the anti-Markovnikov hydration product from an alkene. So let's look at the hydration reaction that produces the Markovnikov product, which just utilizes dilute sulfuric acid. So if we look at the mechanism here, we have our alkene, which is both nucleophilic and basic. We're treating that with acid, and dilute H2SO4 will produce hydronium ion as the acid in solution. And so the alkene, being nucleophilic, will pick up a proton from the acid. This will occur regioselectively to form the most substituted and therefore most stable carbocation intermediate. So the hydrogen will get added preferentially to the less substituted carbon so that we form the more stable, more substituted carbocation intermediate. This carbocation is highly electrophilic, and even weak nucleophiles such as water can do a nucleophilic attack. The intermediate is still charged, so we need to have a final proton transfer step to isolate a stable, non-charged product. So we use water to deprotonate, and the product is then the alcohol and we've regenerated hydronium ion. So we only need a catalytic amount of acid in this case because it gets used in the first step and then regenerated in the last step. So if I had tried to use this reaction on a slightly different alkene, let's say this one here, and we use the same conditions, we might expect to get a similar product, right? But actually this one is not isolated. And instead, we'll get a tertiary alcohol product because this alkene will be subject to rearrangement. So when the secondary carbocation is formed, a hydride shift, in this case, can take place. And that would generate a tertiary carbocation, which after water attacks and deprotonation would lead to this product that has formed due to rearrangement. So in a case like this, it's not ideal to use dilute sulfuric acid because you won't obtain the product that you want in good yield, right? So instead, what we can do to form the desired product, go all the way here, is to use oxymercuration, demercuration. This will allow for the Markovnikov hydration reaction to occur, and the reaction does not produce a carbocation that will undergo rearrangement. So let's look at that reaction. If we take an alkene like this and treat it with mercury acetate, one of the acetates can essentially dissociate from the mercury, leaving it positively charged and ready to react because it's now a good electrophile. And remember, our alkene is nucleophilic. So we can have a reaction where the alkene attacks the mercury and simultaneously a lone pair on the mercury forms a second bond with the other carbon from the starting material. So this is the first step of the oxymercuration demercuration reaction, and it forms what's called a mercurinium ion intermediate. And this intermediate has a mercury which has a slight positive charge, and then this bond between the mercury and the more substituted carbon is weakened, and so they actually share the positive charge. So as a result, this carbon, the more substituted carbon, is electrophilic, similar to a carbocation, but it's not a true carbocation, and therefore we're not going to see a carbocation rearrangement happen. So there's also water present in the reaction, which is a weak nucleophile, but strong enough that it can do a nucleophilic attack. and go through this type of intermediate. Water can deprotonate, and we can lose the mercury acetate through the second step. With sodium borohydride, and that mechanism is not discussed because it's beyond the scope of this class. So after that happens, the product will be the hydration of the alkene, right? And there was no rearrangement. So that's the advantage of this reaction. And then lastly, we'll discuss part of the mechanism for anti-Markovnikov hydration of an alkene to produce an alcohol product. And the reagents for that were BH3THF and sodium hydroxide, hydrogen peroxide. It's a very long mechanism, so we won't be covering the whole thing, but the first step is really the most important because it sets the regioselectivity of the reaction. So we have our borane BH3, which boron has an empty p orbital, so it's electrophilic. And so the alkene, which is nucleophilic, will be able to attack the boron, which only has 6 electrons around it right now. This will occur regioselectively to form a bond between the less substituted carbon and the boron because of steric hindrance. So if you ended up adding the BH2 group to the more sterically hindered side, it's just not as preferred as to the less substituted carbon. And then simultaneously, hydride will shift over to form a bond to the resulting positively charged carbon. So you end up with the hydrogen attached to the more substituted carbon and then BH2 attached to the less substituted carbon. And the second step will really convert, so step 2 converts the BH2 to an alcohol group. And I'm not going to review the steps for that because it's quite a long mechanism. But you can review that if you'd like